The enormous detonation is an idea that outlines how we could translate the universe, framing the supporting flow of cosmology as per Einstein's hypothesis. Furthermore, what is known as coarse-perusing cosmology, the huge explosion, was the moment the universe began its expansion, marking the creation of all matter, energy, and existence. This event occurred approximately 13.8 billion years ago and led to the massive universe we observe today. However, recent advancements in cosmology suggest that the huge explosion probably wasn't the outright beginning. Rather, there could have been a phase before the Goliath blast that was also critical in shaping the universe. This pre-period is known as inflationary improvement. Inflation is one of the most fascinating aspects of modern cosmology. It suggests that before the hot, dense period of the huge explosion, the universe underwent a staggeringly fast, dramatic expansion. During this period, the universe was growing in size at an extraordinary rate. To illustrate how extreme this growth was, if the universe started smaller than a particle, it would have expanded to be vastly larger than the entire observable universe within a fraction of a second, around 1/4,000,000th of a second. This phase of improvement didn't last long, but it played a critical role in shaping the universe. When the inflationary phase ended, the energy driving this growth was released into space, heating it up and creating the particles of matter that make up everything we see in the universe. In many ways, inflation is the precursor to what we consider the huge explosion. While the theory of inflation is widely accepted in cosmology today, many unanswered questions remain. For example, we don't yet understand what started inflation, what caused it to stop, or how long it lasted. These are open questions in cosmology, and answering them is crucial for a deeper understanding of the universe's origins. Before inflation, the universe was an incredibly dense, minuscule spot of matter often referred to as a singularity. From this singularity, inflation began and eventually led to the formation of particles, stars, and galaxies. The idea of the huge explosion as the beginning of everything is compelling, but modern cosmology suggests a more intricate picture. Some theories propose that the universe went through a phase before the huge explosion. During this phase, inflation caused the universe to expand at an extraordinary rate, increasing in size by an incredible factor within a trillionth of a second. This rapid growth was fueled by an unusual form of energy that filled empty space. When inflation ended, the energy that had driven this expansion converted into particles, heating the universe and leading to the hot, dense state we call the huge explosion. This inflationary stage was cold and empty, but it set the stage for the creation of matter and the universe we see today. One of the more speculative ideas in modern cosmology is the concept of timeless inflation. This theory suggests that inflation didn't shut down all at once. Instead, it stopped in patches, creating different pockets, each of which could be a universe in its own right. Our universe would be just one of these patches. According to timeless inflation, there could be an infinite number of these universes, each with its own set of physical laws and constants. This is where the possibility of the multiverse comes into play. The idea that our universe might be just one of many, or even an infinite number of universes, is fascinating. If this concept holds true, it could explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we just happen to live in one where conditions are perfect for stars to form and for elements like carbon and oxygen, vital for life, to exist. While theories like timeless inflation and the multiverse remain speculative, the idea of inflation itself is well supported by observational evidence. The strongest evidence for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was created nearly 380,000 years after the huge explosion, when the universe cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light provides clues about the universe's earliest days, helping scientists understand what happened shortly after the huge explosion and supporting the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images reveal subtle variations in the early universe's temperature, and these variations align with predictions made by the inflationary theory. This experimental evidence strengthens the idea that inflation is not just a theoretical model but a fundamental aspect of how we understand the universe's origins. Understanding the huge explosion and what occurred before it requires combining two of the most important theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets, while quantum theory describes the behavior of particles on the smallest scales. To answer the fundamental questions in cosmology, such as what the universe is made of and what preceded the huge explosion, we must integrate these two frameworks. Where it came from, researchers need to foster a hypothesis that consolidates these two systems. This would permit us to comprehend the enormous detonation as well as the circumstances that prompted it. One of the most shocking parts of the universe is its size. The most far-off objects we can notice are around 47 billion light-years away, signifying the perceptible universe is around 94 billion light-years across. This might seem bizarre given that the universe is just 13.8 billion years old. How could the recognizable universe be larger than the time it would take light to traverse it during the universe's lifetime? The answer lies in the fact that the universe has been growing over time. As the universe expands, the distance between objects increases, making far-off objects farther away than the time it would take light to contact us. Most researchers believe that the universe extends far beyond the discernible universe. In fact, it's possible that the whole universe is boundless in size. The detectable universe is essentially the part we can see, limited by how long light has had to travel since the huge explosion. There may be vast regions of the universe that we will never be able to see. While it's possible that the universe is limitless, the question remains: is there anything beyond the universe? Most researchers are skeptical about this idea. Assuming the universe is endless, there would be no external to it. The universe would essentially continue forever. Even if the universe is finite, it might not make sense to discuss anything beyond it. Beyond would imply something outside of space, which itself is a property of the universe. So, the concept of beyond the universe may not have any physical meaning. Just as the origin of the universe is a subject of great focus, so too is its possible end. The best current estimate is that the universe will keep expanding forever. This is due to a puzzling phenomenon known as dark energy, which is causing the universe's expansion to accelerate rapidly. Before the discovery of dark energy, scientists believed that the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and start contracting, leading to a big crunch. However, dark energy seems to be pushing the universe apart more quickly. If this acceleration continues, the universe will keep expanding endlessly, eventually reaching a state where galaxies are so far apart that they become isolated from each other. In this scenario, the universe would become cold, dark, and empty. Stars would burn out, galaxies would drift apart, and matter would eventually decay. This is sometimes called the Big Freeze or the heat death of the universe. The story of the universe, from the huge explosion to its possible end, is one of the most profound and complex in science. While we've learned a great deal about the origins of the universe through the theory of inflation and the study of the cosmic microwave background, many questions remain unanswered. What caused inflation to start and end? What lies beyond the recognizable universe? Is there a multiverse, and if so, how many other universes exist? As researchers continue to study the universe using advanced technology and theories that combine quantum mechanics with general relativity, we will undoubtedly gain further insights into these mysteries. The journey to understand the universe is ongoing, and each discovery brings us one step closer to answering the ultimate questions about our existence. The investigation of the universe's origins and structure isn't just a scientific endeavor. It also raises philosophical questions about existence, reality, and our place in the cosmos. One significant area of interest in cosmology is the concept of dark matter, which is believed to make up roughly 27% of the universe's mass-energy content. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential for explaining the formation and behavior of galaxies. Ongoing studies and observations have provided insights into dark matter's properties, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, so far, no direct evidence of dark matter particles has been found. As the search continues through a combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter affects the large-scale structure of the universe, we are gaining a better understanding of this mysterious substance. Another key area of research is dark energy, the perplexing force driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total mass energy content. Its discovery was unexpected and has led to many theories, including the cosmological constant and dynamic fields. Understanding dark energy is critical as it will determine the ultimate fate of the universe. Scientists are studying its effects on cosmic structures and trying to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation provides valuable insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter has clustered together under the influence of gravity, leading to the intricate structures we see today. Simulations run on supercomputers help scientists understand how these structures formed over billions of years and continue to evolve. Astrobiology also intersects with cosmology, as researchers seek to understand the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets lie in their stars' habitable zones, where conditions might be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet hospitable to life. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories like string theory and loop quantum gravity aim to bridge these two domains, offering explanations for phenomena like black holes in the early universe. As technology advances, so too does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe, providing unprecedented detail of distant galaxies and cosmic events. With each groundbreaking observation, we come closer to unraveling the mysteries of the universe's formation, evolution, and ultimate fate. The exploration of the universe is a rich tapestry of scientific inquiry and philosophical reflection. From the fundamental forces that shape large-scale structures to the search for extraterrestrial life, our investigation is a testament to humanity's enduring curiosity about the cosmos. As we strive to answer these profound questions, we gain a deeper appreciation for the vastness and complexity of the universe.